Hi, everyone. Welcome to our bi-weekly webinar. Presenting today, we have Brian Hughes, our president and co-founder, and I'm Michelle. I'm the business development specialist here at Sologic. We're going to be walking through a reliability RCA example problem. Most likely, it'll be Brian not making things from scratch, but your inputs, questions, feedback are definitely highly appreciated. So feel free to ask questions or post in the chat. I'll be moderating this webinar, so I will interrupt as needed.
Interrupt as needed, and no doubt about that. So I'm not going to just make it up actually today. So I'm better prepared than that. So okay, well, I appreciate everybody joining. Let's talk a little bit about Sologic as we get rolling here. If you've been on other webinars, you probably have seen me talk about this stuff before. So apologies in advance. If you have not been to one of our webinars, we do these every other week and we do them for free and we record them and then we post them. And if I'm on my game, I write a blog entry about what we talked about and then we post it on the site. I will admit I'm a little behind on a few of these blog entries, but that said, the recordings are all up there from past webinars. And if you've got a webinar topic that you would like us to cover, then no problem. Happy to do it. In fact, Michelle and I were just talking, and you all heard us because we just talk, right? So, leading up to, we had a question come in this morning, and actually, it was a really neat opportunity for us to add a little content to our library, and it was turned out to be really helpful. I get to learn a little bit about a new subject, which I always like to do, and then we're able to provide value to you folks, our broader client base, which is our sole intent behind these webinars. I and Michelle are based here in Seattle, along with the majority of our Sologic and Causelink team. But we've got, I see Ben Peardeman is on the line. He's participating today, so you won't hear him talk. But Ben is in Ireland, and Ben is our business development manager for the EU and the UK and the EU, and probably for other areas too. So we just brought Ben on board recently, and welcome, Ben. It's really fun to have you. But we have other offices in different parts of the globe, and we're able to support you wherever you are and whatever it is that you do. We work in a ton of different industries, and we also work with multiple disciplines across those industries. And what that allows us to do is bring our root cause analysis, our structured problem solving process, or whatever you want to call it. I think I've been running with organizational learning lately to all of these different companies. All of these are our clients, just a sample. We have a ton of clients, all of whom we're very proud of, and we are happy to work with and are grateful to for the business, but also the opportunities to learn both how we would apply structured problem solving, organizational learning, or whatever to a variety of different industries, a variety of different company cultures, a variety of different disciplines, all using that same core methodology. But today, we're going to be focusing on reliability and maintenance. And I thought what might be nice is to start out with an overview of what is reliability and maintenance, what's its purpose. And if you are a reliability and maintenance person, you probably already know all this stuff, but maybe you're not. Maybe you're from a different discipline or a different area, and you're not necessarily familiar with how reliability and maintenance works or what it's supposed to do. Mm. So the first bullet point that I have is to ensure functional reliability. That means we want our assets to perform their required functions in their operating context. That means, like, for instance, I've got this asset of a Yeti mug, and I need it to keep liquid hot, or whatever. I guess I could put soup in it or whatnot in the operating context in which I plan on using it, which is mostly my office or around the house, right? Hmm. And and there may be some other things that I needed to do as well. So I want to define what that is, and then I want to have a maintenance strategy, a reliability and maintenance strategy that allows for that asset to continue as long as possible, or as long as I expect it or need it to do what it needs to do. Also optimizing investment in uptime. All right, so I think there's a misnomer around reliability that says, well, we want this thing to run forever and forever. Okay. And that may not necessarily be what we really want because it may be that it costs way too much for us to actually achieve that goal. So, what we're trying to do with reliability and maintenance is optimize our investment in what it takes to keep an asset up and running. So, we're going to balance reliability with cost. So that we're achieving the right level of uptime at the right cost, not just maximizing uptime at any expense. So there's a real sort of symmetry and balance to a well-designed and a well-run reliability program. We are trying to protect safety as well. We need to identify and mitigate maintenance-related risks that could endanger people. 100%. So yeah, we want to optimize uptime. But at the same time, we also have a direct insight into risks of safety, risks to operators, risks to people walking by, risks to ourselves as maintenance professionals, et cetera, et cetera, et cetera. So certainly there's a safety component to reliability and maintenance. Also, the environment. So protecting failures that could cause spills, emissions, or other environmental harm. Because when these things go to bits and go to pieces, well, depends on what's inside them. But if what's inside them shouldn't really be outside, then we have an obligation to protect the environment through our reliability program. And then also to support strategic decisions, prioritizing maintenance strategies, preventive maintenance versus predictive maintenance versus run to failure versus we need to redesign it so it does something different or whatever. And all of these based upon failure consequences. And so all of this stuff is the world of reliability and maintenance. And hopefully I've said it in words that you can relate to, and in words that hopefully sort of match your mental model. And I'll leave room for interpretation that there's more to it than what I've just said, maybe a little less to it, or maybe it could be said a little differently. But all in all, should get us set where sort of in this world of reliability and maintenance before I move on to discuss how we approach reliability and maintenance related problems through the lens of Sologic. All right, so at the highest level of abstraction, I do always like to start out with saying or defining what it is that we mean when we talk about a problem. We discuss problems from the standpoint or from the perspective that it inhibits significantly our pathway towards goal. Okay, so if we're in this space where we want to be and we want to end up over here, we've got this goal that we want to achieve. We often have this imaginary plan of the steps we're going to take and the path we're going to walk in order to go from where we are to where we want to be. Now, invariably, our actual paths will meander a little bit, and that is because of uncertainty. There's uncertainty in a variety of different areas, and we discuss uncertainty in other topics and other webinars, and so I'm not going to go into great detail in this webinar. But the truth is we just don't know what's going to come our way, so we plan as well as we can, and we build resiliency and all of that. But at the end of the day, we're going to be learning as we go. And actually it really is it's a testament to our workers who we entrust with the plan and then entrust to know when they need to deviate, how they need to deviate, how they need to modify, adapt, overcome in order to get where we need them to get in a timely manner. So this is the normal way that things actually happen. But sometimes we see things go significantly off the rails. We have a significant deviation, and then we call that a problem. Yeah, it's a problem, and it can come in a variety of different forms, a variety of different flavors, and whatever that problem happens to be, we're going to make an investment in bringing that problem back to heal so that we get on path as soon as we can, and also so that we don't end up with such a substantial deviation in the future. And typically, that's where we're going to apply root cause analysis, and it's no secret that we do that in the world of maintenance and reliability as well. I do want to take this just a step further and talk a little bit about how significant a deviation might be. I made this up a month or so ago where we take the same sort of I guess model and kind of mess with it a little bit to see a minimal deviation might cause. Like maybe we just dip below that threshold line for a minute. And it's like, yeah, was that a problem? It was, but substantially not really. I didn't like it, but I don't want to see that happen again. But at the same time, it could have been a lot worse versus something that looks like this, where you have a substantial amount of area below the threshold, and so representing a substantial loss. And so in those cases, it gives you an idea of characterization of what different types of problems might be and the magnitude of different types of problems. And the way that we characterize magnitude is through impact. And reliability and maintenance problems are they're no different. We look at the problem, we look at the impact of the problem, and what's interesting is we look at with reliability and maintenance. Not only are we trying to keep problems from occurring, we are trying to recover from problems as quickly as possible. All right, so. What you're looking at on this screen is a variation of what we would normally call the PF curve or the PF graph or whatever. And normal, when I say normal, normally speaking, what we see with the PF curve is really just what you see in the yellow area, and then the red area, where you see this drop off in performance that drops off below a minimum acceptable performance level. All right. So, but I like this one because we can see the phase below that or before that. This green phase is where we want to be, where everything is operating at a level that where you've got some margin or some buffer above your minimum acceptable performance level. This is great. This means that things are humming. Everything's working great, no problem. We may see what's probably true, y'all, is that we see dips and variations kind of like back here along the purple line, right? So it may very well be the case that it is normal for there to be normal variations, all of which taking place above that minimum acceptable performance level. All right. So what we're doing here is we're listening, watching, and trying to make sure that we're applying the minimum amount of maintenance and effort to maintain this level, this comfortable level of margin. All right. So when we start though to see a deviation, that's where we enter this corrective phase. When you enter the corrective phase, you start to see, or there starts to exist, whether you see it or not, a degradation in performance of the asset. Okay. We have monitors in place for this. Things like well, I mean, we monitor based on our eyes and ears and other senses based on reports from people, based on walking around and observing and auditing and conducting visual checks, etc. That's one way where we can identify detections in degradation. We can also do that through condition monitoring devices such as vibration, temperature, other types of alarms, or watching trends, data trends, operational trends, etc. That because the idea here is that if we identify deviations that are outside of our normal, what we would consider to be our normal variation in performance, that indicates a degradation or the beginning of a degradation towards failure. And so this is where we have a degradation towards functional failure. Functional failure is where we cross this minimum acceptable performance threshold, but we're still performing. Okay, so it's performing, but it's not doing what it needs to do. And we're going to talk about that in our example today. I'll just give you a little hint as to where we're going. We're going to look at a heat treat furnace where part of the heating components fail, not all of them. So the furnace is still furnacing, so to speak. It's still operating, but it's just not maintaining that minimum acceptable performance level. But it also includes complete failure, 100%, dead in the water, not operating at all the way to complete failure. Once you reach this phase where you've gone below the minimum acceptable performance level, we are in that purely reactive phase. We are now in it, in the weeds, and are doing our very best to nurse and coax and fix and bring that thing back online as quickly as possible. Okay, so kind of gives you an idea for our goal for maintenance, going back to the beginning, is that we want to stay in this proactive mode and we want to extend this as long as is feasible with respect to our constraints. Okay, so hopefully that puts you all into the same mindset. Um, I think at this point, what I'm going to do is just sort of shift directly up into the causal template or setup that we use when we're looking at asset impact or asset downtime. Okay, so when we're doing cause and effect analysis, we always start out with the focal point. The focal point is the problem that we're investigating. And what we've found with maintenance reliability related issues is that many times, most of the time, it's nice to template that focal point. And so the template looks like this. What's the asset? Name it. And then how many hours did it take to recover? Name those. Put a number on that. And then what that allows us to do is to immediately branch into what we would call the fault path. That is the story behind what caused the asset to go down. And the recovery path, which is the story behind why it took as long as it did to fully recover. And I want to make sure to illustrate this point. The recovery path doesn't always have to be a sad story. Sometimes it's a happy story because imagine this for a minute. You got some asset that goes down, but then you have a maintenance crew that heroically identifies it, brings it back online, minimizing the downtime, creating something that looks more like this than something that looks more like that. Okay, so if you what you did has actually minimized the downtime, I think it's well, I want to, and if I were running the maintenance department, I would be asking people, listen, I want to know the good stories. I want to know what you did in order to recover, and I want to know why you were able to do that, right? So, did you have good troubleshooting guides? Did you have good access to expertise? Did you have access to labor? Did you have all the spares that you needed? All of that kind of stuff, because knowing the good stuff allows us to reproduce that in other parts of the company, and it also lets us tell the happy story, at least that part of it. So now, if it's on the other side of the fence, then I want to understand what it might take for us to do a better job at recovery. But maintenance and reliability is not just preventing failures, it is also recovering as quickly as possible. And when you look at it in light of this particular graph, so it's not just preventing a degradation in performance, it's recognizing it early and then responding in the right way such that we ultimately end up minimizing as much as possible the negative impact. And so we do that through, if we do that through, my PowerPoint's just running around on me. This is not me. This is my day. We do that through an understanding of what caused the failure in the first place, and also explaining the recovery time. All right, that's enough of a setup. So looking for questions and don't see any. So good. I must have completely beat that thing to death because you guys don't have any questions. You want to jump into the example? Okay, we're going to do that. I want to set the scene here though, and this is a fictional example based on, I guess, real life scenario. So we're not using. I didn't actually investigate this. We made this up, but it should be pretty good. All right, so here's the story. We're talking about a vacuum heat treat furnace. Okay, and it's used to harden aerospace grade titanium alloy components. So imagine a bunch of stuff that goes into engines. Airplane engines, rocket motors, whatever, the cool stuff, right? Made out of titanium and a special titanium alloy. And part of the process here is once they cut and shape these parts, then they're going to throw them through a heat treat cycle, so that so it optimizes the material for peak performance in those extremely, I guess, hostile environments for materials. Okay, so during a production run, the furnace tripped offline due to an over temperature condition. The safety interlocks engaged and shut the system down. So it saw a runaway temperature condition, and then certain safety interlocks that were in place exactly for this purpose engaged, and then they shut off the furnace. Now, impact and consequences. There were no direct injuries as a result, but electrical work under pressure increases the risk exposure. This is often sort of the unspoken risk to maintenance and reliability outages. And here's how it works. All right, so your gear goes down at a time that you don't want it to. And then operation starts screaming because they don't know what to do, right? All they want is the thing to work, like the thing is supposed to work. They push the green button and it does its thing. They push the red button, it stops doing its thing, and that's pretty much all they know about it. Maybe not, but I know I know who my audience is today, so I'm going to be a little harsh on the operators. It's not always their fault, dude. Anyway, so but then there's this big hurry up, right? Like leadership gets involved, and they're what WTFing, and they're screaming at maintenance leadership, who's screaming at you, get your stuff, get your tool bag, get your spares, get out there, fix it, so the operators they can push the green button again, because this soon as they get back up online is what they care about there. All right, well, there's a lot of pressure. And when you're under a lot of pressure like that, and in particular when you're working on equipment, which is, maybe is a little bit dangerous, like a heat treat oven, which can be real hot, and or involving closed spaces or other kinds of things, then you're working in an essentially higher risk operating context. And I think that it's very important in a root cause analysis to always recognize that under pressure, people are at greater risk. And by greater risk, what I mean by that is there's more opportunity for I guess uncertainty to throw curveballs your way, and for some of those curveballs to result in injuries. Okay, so it's better to have a planned job, a planned maintenance activity, because the planning decreases the risk. The planning increases certainty and thereby is less likely to result in an injury. So we always want to consider the fact that these folks are in there doing this work under pressure, which does increase their risk exposure. Okay. Now, no environmental in this case, no spilling of oil or releasing of fumes or I don't know, whatever else. But the furnace was unavailable for 48 hours. That caused a bottleneck in production and a backlog of a week. It took them a week basically to recover from those 48 hours down. In the economic front, it was an in-process batch of they lost $75,000 worth of scrap parts that were in the furnace at the time, plus expedited shipping, which cost them 8 grand, plus overtime, which cost them 15,000, plus late delivery penalties on the contract for $25,000. So certainly an economic impact there, and then also a potential regulatory or compliance related issue. They logged a recall but not executed. Could be major nonconformance risk, right? So let's say that they did. What if these parts ran at either the higher temperature or even a lower temperature, but some off-spec temperature? Now you got a quality control problem. And if you aren't aware of it and you ship those parts to your customer, now you got a quality escape, you got a major nonconformance, you got a potential reportable to the FAA or to other audit or regulatory bodies, and bam, 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 now you got yourself a real issue, right? So this furnace running out of compliance, we want to think about the impact of this particular event in all of these different areas. Okay, so let's do this. So I'm going to switch over to CosLink. There it is. Oh, real quick orientation for you. CosLink, if you've not seen it before, it is our browser-based RCA application. Here, let me log out, and then I'll show you what it looks like when I log in. There. Now, I'm logging in through the login screen that it ships with, but oftentimes in our clients, there's a single button here because we hook it up through single sign-on. But I'll just do this. I actually use a password, and I'm not scared of showing you my fingerprint. I don't think it's going to help you if you have nefarious purposes in mind. Okay, I'll zoom in a little bit. And it brings me into the dashboard. The dashboard shows me things like my recent RCAs, who's been doing the most RCAs. Look at that. In the last 3 months, I'm one behind John. So I think if I do two today, I'll catch up. Then I'll be in the lead again. Other types of summary reports that are summaries of reports that I can configure myself. We do have an FMEA module for you folks in the maintenance world, which I'm not demonstrating today, but we do a ton of FMEA work in the world of reliability and maintenance. So if that's something that you're interested in, let me know. What I'm going to do though is go to RCAs, and then I've got my example right here at the top, and I'll click to open, and it will take me into the overview page. But that's not where I want to be. I want to jump to evidence. So 5 steps in our Sologic process: gather and manage evidence and data, write the problem statement, analyze the causes of the problem, identify solutions, and then produce the final report. Okay, so I went ahead here and added some evidence records. Evidence can be things like statements from the operator, supervisor, engineering. So what I would do, I would probably write these statements up as attachments, where you can see I have access to attachments on the left in the sidebar. So I can upload a variety of different attachments that I might use in several different areas of the RCA. All right, but I'm going to jump back to evidence. And what I would do is write those up in Word or something like that. And then I would upload those documents as attachments, PDF file, Word file, or whatever. And then I would attach them right to that record so that I have them available. System data. So that might come through as a .csv file or a tab delineated file or something like that, or maybe a straight up Excel spreadsheet or some other form. And then I could upload that as well. And then also, I want to see scheduled maintenance and job data that comes out of Maximo. So if Maximo is our maintenance management system or whatever it happens to be, I want to see what the PMs were like on this equipment, what was done, what wasn't done, what was scheduled, and what happened, what was if there are any notes or any anomalies or things like that. I want to check that out. And then also, you will find that there was a notice of recall that came from the supplier. Okay, so lots of different evidence items. Listen, I go in and I audit RCAs all the time in client systems that I have access to. And some of the folks that are doing these do a really good job at data collection and evidence. Some people, maybe they skip that stuff. So I'm not ratting anybody out, okay? But I'm just gonna say, if you're somebody that skips the evidence step, mm, don't do that. You should capture your evidence. It's might feel like it slows the process down just a little bit. Maybe it does. But that process of slowing down, deliberately thinking, what is my evidence? What am I basing conclusions on? What am I using to to basically either support or refute the hypotheticals that invariably come up in a cause and effect analysis? How do I know that someone's telling me not only the truth, but how do I know that what they're telling me is accurate? I just have been burned too many times myself, right? So I will never skip this step. I will always take a few extra minutes to gather my evidence, to pull it together, to put it here in CosLink. or wherever. In fact, I maintain a secure offline folder for every investigation that I do that has my evidence neatly organized, neatly labeled. Believe it or not, I absolutely 100% believe in process when it comes to organization around your evidence folder. And it always ends up here no matter what. And as much as I can, I preload it before the meeting. Okay, so that I walk into the meeting with my evidence all organized, all in line, and then maybe even a list saved under tasks of evidence that I still need to gather or questions that I want to ask or whatever, right? So I will log that in the tasks report and make sure that I ask those questions in the RCA. Okay, so hopefully I've made the case for evidence. I mean, literally, it is the foundation upon which everything else is built. So don't skip it. Problem statement. Okay, well, problem statement is the information about the problem. So here I have the focal point. Remember what I said about focal point with maintenance related issues. Here, I'm going to jump back over here. I'm going to go to my little template. Asset down, X hours to recover. Well, did I follow my own advice? Vacuum heat treat furnace. Well, I didn't say down. Here, let's say unavailable. All right. Required 48 hours to recover. I immediately go there with reliability and maintenance related problems. I immediately use this format and it pretty much always helps me out. There are edge cases when this isn't going to work out so well, but the variety of machine downtime related things that you're looking at are going to be in this format. Can I just talk for a second about why do I say vacuum heat treat furnace unavailable? Well, because assets fail often at the component level. All right. So I could instead say that why wouldn't the focal point be something like, well, my relay, my solid state relay failed. That's the focal point. Well, the solid state relay is the component. We're going to find out that the relay is what failed that brought the vacuum heat treat furnace down. But the relay itself is while it may be the thing that brought the asset down, the fact that the asset is unavailable is important because the asset level is where we experience the impact. Otherwise, just a component that failed. And so, and by starting, and when I jump over into the cause and effect analysis, you'll see that by starting at the asset and working my way to the failed component, and then beyond the failed component into the causes of that, actually serves me very well. So asset, not component. Downtime, okay? And then I'll show you the template at work when I get to the analysis part. I've got my start date and my end date. I've got my start time and my end time. I've got my investigation start date, which shows the gap between how quickly we were able to activate our investigation process. This has a lot to do with the maturity of your RCA program and a lot to do with whether or not you have event-based triggers in place that tell you or your teams when you're going to do a root cause analysis, either based on actual outcome or based on risk. Okay, so I like to base my RCA decisions not only on actual outcome, but also based on risk. And the reason is because the causes of a potential problem that had significant risk are often exactly the same, but for a couple of slight differences to problems that actually had significant outcome or significant impact. So because the causes are almost exactly the same, I look at them as really neat opportunities. I really love to investigate near miss examples. And I also, especially with respect to reliability, I like to bring this risk assessment or some kind of a risk assessment score into the discussion because this tells me that for my solutions, I should be looking for ways to reduce consequence as well as for ways to reduce probability. So both of these are opportunities for me to reduce risk overall, and I want my solutions to be addressing those. All right. So then I look at where, with reliability, it's almost the easiest way to document where the problem happened. I pick location, asset, component company, right? Maybe I moved the company up a couple of levels, but here we go. This tells us exactly where the problem happened. And then under impact, I have safety, no direct injuries. Environmental, no impact in this case. Here are though for production, I've got 48 hours lost in bottleneck process. This is a bottleneck process, meaning that things that the parts must route through the heat treat furnace. That means that everything else is going to back up on the other side of it. And so any downstream work that I have, if it can't fulfill my orders that I've got, and if my inventory doesn't, if I don't have existing inventory to fulfill my orders, well, that's going to be trouble. Okay. And it took it took about a week to come back from this 48 hours lost. Why? It's because you have to produce for your existing orders as well as for your backlog, and it's going to take a bit. That's going to involve overtime of $15,000. Also, you're likely going to scrap. If you got your parts too hot, then I don't know. There's going to be standards that have to be adhered to in these highly critical parts and pieces of equipment and components. I don't know. Are you going to put parts that didn't go through the exact recipe for heat treat into your rocket motor? I mean, no. No, I'm not. I'm going to scrap it. It's not worth it. Mhm. I've got expedited shipping and I've got the late penalties. Remember, we talked about those over here. Okay, so in the write-up. All right, so let's continue. Oh, I've got my potential impact down here, and this is where I've logged the potential for risk exposure to the workers for working under pressure. Great. Then let's move on. I'm going to go to the cause and effect analysis. All right. Now I built most of this out already. Here, let's do this though. I'm going to collapse. I could have built it with you one step at a time, but I don't know. I got excited. I built it out this morning and I thought, oh well, I'll just share it with you guys. That's we'll just build it together this way, which will be a little easier. And actually it'll keep us a little bit ahead of schedule too. So, all right. Well, remember I said we're going to break this down into fault path and recovery path. Check it out. Let's get a little fancy. For fault path, I'm going to color it this kind of red color. Recovery path, I'll make it this green color. There you go. So if you want to get fancy, you can. All right, well, so note here that my furnace shut down because my safety interlocks tripped. That is the direct cause of my furnace shutting down. Imagine you standing in front of it. You're like, look at my beautiful furnace doing its beautiful thing. And then it's like, and it starts to shut down. You're like, wait a minute, what's going on there? And you find out that the safety interlock's tripped. Let's go ahead and just see why that happened. Well, that was because there was an over temperature condition in one heating zone that was detected. And what's true about those safety interlocks is they worked as expected and as intended. This is a very important detail. The safety interlocks did shut the system down, and they did that in response to an over temperature condition. That's because they did their job. When you think about it, those safety interlocks are a barrier or are a level of protection that are put in place to detect and contain a situation exactly like this. And in this case, they worked. Imagine for a minute, though, that the safety interlocks had not worked as expected or as intended. Well, now that's a different story. Now we're going to be blowing this branch out to try to figure out, well, geez, what went wrong with our safety devices? But the fact that they worked is important here. And I think that it's important for us to explain that, right? So if you're not familiar with Sologic, we are looking at branches. We're not using one-for-one cause and effect relationships. In other words, we're not just saying that the interlocks trip because we have an over temperature condition detected in one zone. We are going to call out the fact that safety interlocks exist and they also worked. in response to this overheat, which caused them to trip. And it took 48 hours to recover. Therefore, our furnace is down for 48 hours. All right. So we're leaving no stone unturned here. Let's go ahead and I'll blow it out one more level. We have that over temperature condition because the heating element shut down, and the heating elements are required in order to maintain that consistent temperature. Okay, so now the reason that the heating element actually it didn't shut down. Heating element went into a runaway condition. All right.
And we have Larry noting that this is a paradigm here. Sometimes thinking only goes as deep as the interlocks function, not going deeper into the actual failure.
Well, that's a good point, Larry. So let me unpack that as soon as I correct my logic here. Um, I'll just say, heating element, I'm gonna say, upper temp, limits, cannot be exceeded without compromising quality. Okay, so I'm going to say that. So we've got this heating element runaway condition, and Larry said sometimes we just say that the safety. If I can if I can sort of translate my own brain into Larry's brain, which is not always it's kind of a scary place. I guess the part that I'm in, it's not so scary today. So Larry, basically saying don't stop. I think what Larry is saying, and you can comment and see if I'm right. Um, the safe, I think what Larry's saying is like, hey, guys, we had this thing happen today, but the safety interlocks did their job. So good thing we did that. Let's just get back to work. Right. So we would stop right here and basically say, hey, I heard you guys had a thing today. Yeah, it's true, but interlocks kicked in and prevented it from, from going too much further. So I guess, we're just gonna replace that relay and we're gonna call it a day and not really examine it further. And that's, I think, what Larry is trying hard to get people to see is that, hey, let's take that further and really not you. The fact that they worked is great, but we still want to understand at a deeper level why that over temperature condition happened. So we've got this heating element and runaway condition. That's because we had a solid state relay failure, and relays are what control or regulate the power to those heating elements. That's a bit a bit of additional information. The fact that relays are the things that control how those elements operate, and we have a failed one, that combination together resulted in that runaway condition. Okay, so I'll click and we'll expand this a little further. The relay failed because it overheated. And there actually is a quality issue known with this type and batch of relays. And that relay was not replaced as scheduled in Maximo. So we went and did our homework. And that was because the recall paperwork was received and the work was scheduled, but the maintenance crew prioritized other work over this. Okay, so now we're kind of at this point where not only do we have a failed component, it overheated, right? And we see also that we were aware that this component was at risk, and we did schedule the work, but we ultimately didn't do the work. This is pretty slippery in terms of a slippery slope towards blaming the maintenance crew for this terrible decision. Okay, but what we're not going to do is we're not going to blame them immediately. Only after a fair trial, right? No, we're not. We don't want to, we want to make the assumption at least first that that there was a reason behind that. So we need to be really careful about how we set the scene here to make sure that the conversation remains productive and doesn't shut down. If we're in a blame culture, this is going to be as far as you go. And a lot of times we're going to pin this on the maintenance crew for not having replaced the relay as was scheduled. It's your fault. You're the root cause of the problem. but we want to take this further. We do not want to do what I just explained. Okay. And we may well want to understand a little more about the quality issue with that type of relay. Oftentimes we won't. It'll be up to the electric company who made the relay in the first place, and it's going to be up to them to provide us with that report. Okay. Now, this is a really neat place to include artificial intelligence. So what I'm going to do is I'm going to turn on my lightning bolt, and I want to hear what are some of the AI suggested reasons why that relay may have overheated. So when I click it, it thinks for a second. Ah, yeah. So it's speculating that dust accumulation on the heatsink might be possible, or that there's incorrect relay sizing for this load, or that it's missing some kind of thermal compound, or that there was ventilation blockage, which otherwise would have caused the relay to otherwise would provided the right cooling level for the relay. But remember, we said that this was a quality related problem, so it's not a vent blockage. And so what I'm going to do is I'm going to go to properties. I click here on this three bar menu, go to properties, and I'm going to say disproved. I also know that we have the correct relay sizing. So I'm going to disprove that one. And then also, while possible, in other examples, dust did not accumulate on the heat sink, and I'm going to call that one as being disproved as well. But I'm going to leave this one. And I'm going to let my AI suggest some causes on that one too. So what missing a thermal compound, right? So not this one, not this one, not this one, but maybe this one. Okay. So there might be a couple of plausible ideas here, and I'm going to keep my plausible ideas, and then I'm going to roll forward. So now, just a word about AI. Here, let's do one. I'm going to do it down here too, on the maintenance crew, prioritizing other work. All right, give me my blue box. There you go. Okay, so these are actually these are worth considering. Do you have a high workload from emergency repairs? Are you understaffed? Is there no backup system for tracking maintenance? I mean, that's a valid question. What about an unclear maintenance task prioritization? Are any of these possible? And if so, were any of these present? And so with AI, y'all, we do have it returns four options. We optimized around four. It could return 10, but that we were finding that was too much. And then it could return two, and we were finding that that was too little. So we're optimizing around four. We've also shaped it such that we want it to be helpful and not point fingers and not go down that trackway of blame, punish, etc. It can get off track a little bit, but for the most part, we find it to be extraordinarily helpful. And but you notice that I did not turn it on until I got to the end of my cost path, right? So that's how we use it. That's how we recommend that you use it, that you give it some context, that in collaboration with a skilled facilitator in a team of knowledgeable experts, that AI becomes another expert on that team. And it's extremely useful. If you're like, I don't know anything about this stuff, and then you just like, tell me AI, what is it? Tell me AI, what is it? You just AI your way through your chart. Oh, it's going to be garbage, so you need to work with it. You need to consider what it tells you and not just take it at face value. All right, here, let's dig in down here too, because you want to see the recovery path. I think we understand the story of why these interlocks tripped, but now let's look at the fact that it took 48 hours. I like to make this a math problem. It took 18 hours for stabilization and notification. That's because securing the furnace, lockout, tag out, notify, keyway, quarantine, that's $75,000 batch, all of that took a couple hours. And also we needed to have a controlled cool down of 16 hours. That is the amount of time it takes before we can safely enter the place and enter the furnace and replace that relay. It took us about 4 hours to troubleshoot and diagnose. It took us 14 hours to repair, and that was because we needed 6 hours to complete the repairs and required inspections, but also another 10 hours because we did not have the spares in stock. We needed 8 hours to procure those spares, It also took us a couple hours to dig in and figure out, whoa, these things were under recall, and to basically do that research. Okay, so all of this in terms of procuring spares, it's because we didn't have them in stock. This actually may be a good spot for AI as well. So I'm going to go ahead and get rid of that. And now I'm going to turn it back on and tell me what you think. Let's see what it comes up with. Inventory tracking system outdated. Minimum stock levels not defined. Bam. Supplier lead times not considered. Puh, absolutely. Not budget constraints. The tracking system is not outdated. So these are the two that I kept. I'll just we'll take those out a little bit further. All right, so then we had 4 hours for startup. We had 6 hours for validation. So when you add all of these up, that explains why it took 48 hours to recover. All right, and it also allows us to identify solutions, which we're going to work on next, to help both keep this sort of problem from happening again, as well as allow us to more quickly recover from it if it were to happen in the future.
And Brian, I just want to make sure that you're aware, we have about 5 minutes to go through solution before we open up for more questions,
Yep,
um,
let's do it.
wrap up.
What do you want to do to fix the problem, Michelle? Do you have any ideas? Are you like, no?
Well, I'll leave that to you or our AI.
Yeah, yeah, let's do this. So you guys, what I'm gonna do is I'm gonna let the AI suggest solutions, and then let's see what they look like. Usually does a pretty good job. But again, I would not just put it in the hands of the AI and just let it drive, but implement proper thermal compound application procedures and training. Okay, a little vague, but valid. Establish and maintain adequate spare parts inventory based on lead times. Again, a little vague and valid. So I'm adding those. And as I add them, it's going to add them down below. I'm going to look for a few more. Define and enforce minimum stock levels. Um, I'm trying to think of what's the difference between these two. I'm going to add it, and maybe I'll collapse those together as we review and refine. Let's dig in here. Improve quality control for relay selection and procurement. I I think this is worth considering. I want to dig into that a little bit further, but I'm going to add it so that we do that. And actually, quite a lot of these are looking pretty good as I just scan them. But as we add solutions, what we do at this point is we check them to make sure, is it going to be effective? Is it something that we can do? Does it provide a viable return on investment? And are there any negative impacts that implementing this solution causes? And if so, can we successfully mitigate those? And so we're looking for yes answers all the way down, which then allows us to select, which then triggers us to gain approval, which then triggers us to complete, and then finally to validate for effectiveness at some later point. And that is the complete solutions process. And then after that, we write the report. And of course, you guessed it, we have AI here too. I'm going to let the AI write it. I actually am a fan of writing my own reports. I feel like it slows me down a little bit, lets me write out what is there and solidify what I think I understand about it. But this does actually a very nice job of it, of summary statement in any case. And then when everything's said and done, we can bundle it into a PDF. I'm going to take the report, the chart. I'm going to check on report. I want the detailed version. I want my solutions. And then I'm going to look at the chart. And then I'm going to click create PDF. And then that allows me to share. Click to download. And it looks like this. And it looks like this. There we go. Yeah, so it pulls everything together into a nice, neat PDF. And so, yeah, I will just, in summary, say that with reliability and maintenance problems in real life, here's what we're doing. We are actually providing and recommending that people use a template, such as this one. It goes beyond the goes beyond the recovery path, fault path, and the template that we like is at least one form of it that works good. So you've got focal point, you've got asset and recovery time, fault path, recovery path. Fault path just stops right there because you can't really template it any further than that. But then the recovery path, we look at safety time, we look at diagnostics, and we look at repair. Sometimes we'll include startup and testing in there as well, validation and release, so that it looks kind of like that. All right. But then when you give people a template, which we will be talking about apparently in a future webinar, oh, it makes life so much easier. And we can do templates on a lot of different things. Okay. So look at that, Michelle. 5 minutes left. Any comments or questions from y'all? Yeah? You want your 5 minutes back? I'll give it to you.
Tony said we need to keep in mind that we'll not keep any AI causes or AI causes on the chart just because they sound good. Every
Mhm.
cause that will remain in the cause and effect chart will do so because it's supported by evidence that you discover and attach.
That's right, Tony. Yes, sir, that is correct, buddy. Uh we're not gonna we want to make sure that like just because AI gave us these causes that we also support that with evidence. It's a really important point. And if we can't support it by evidence, well, then that should play into whether or not we leave it on the chart or whether we caveat solutions that we associate with it. Yeah, really good point. Well, all right.
With
Have a
that,
weekend. With
yeah,
that,
thank you everyone for attending our webinar. If there's more specific topics or subtopics that you're interested in the field of reliability and maintenance, Brian's more than happy to dive into those. We do offer failure mode and effect analysis consulting and training. It's not our most well-known product, but it is definitely something that we're happy to schedule a deeper discussion for. So please reach out if you have any questions, and thank you for attending.
yeah, and come to the next one. Check it out. You can come. We'll talk about templates a little more. We'll do a quality assurance template. We'll do a reliability and maintenance template, so it'll be a little bit of a repeat for you guys. Maybe we've done some for aircraft damage and for injuries and all of that. So these templates can be super, super helpful, and that'll be the subject of the next one. All right, cool. Well, let's call it a day then. Look for the recording. If you know anybody that would like to see this on repeat, then you can forward the recording to them. And really appreciate your attention. Hope you have a great weekend. See y'all.